In chapter 4, we are going to study how the actual computer works, especially the CPU and the main memory. So using a simple computer model, the author designed a very simple model called marie, acronym for that is machine architecture, that is really intuitive and easy. And through this model, we can understand a very complex computing system. The model itself is a very simple though, but it's good enough for us to understand the actual computing system. So the marie architecture has the following characteristics. First, the number system uses is a binary, and for negative numbers, it uses 2's complement data representation. It has stored programs. So programs are stored in the memory, and it is a fixed word length, both data and instructions. Data is a 16-bit word, so each word has a unique address. So it's 2 bytes word one, and then address is given to each word instead of a byte in this model. And the instruction has a 16-bit. Out of 16, it is a 4-bit for operation code, which means 2 to the 4, which is 16 different operations or instructions are possible in this model. So it is a very small number of instructions. Even not all 16 cases are used, so we will study in detail later. And the remaining 12 bits are for address. Here the address means when you do operation of addition, then we need to locate where the data is. For that purpose, we use a 12 bits. So 12 bits means 2 to the 12, which is 2 to the 10 times 2 to the 4. 2 to the 10 is 1 kilobytes memory. So 2 to the 2 means 4. So overall, we have a 4K words. Since we have a 4K address spaces. The arithmetic logic unit has a 16-bit as well, which is the same as data words. So arithmetic logic unit uses any arithmetic operations defined here, so addition, subtraction, and then some logical operations that are performed in ALU. And it has 7 registers. A register is a high-speed memory within the CPU. So 7 registers are there. So here are the 7 registers. First, accumulator. Accumulator is one of the two data in ALU. So ALU, arithmetic and logic unit, suppose we do addition, we need the 2 data. The one of the 2 is always from accumulator. So accumulator is one of the most popularly and frequently used registers. And the other data is from the main memory. So we have address for that and the like. So to read the data from the memory, it only reads into the accumulator. To store data into the main memory, the data should be in accumulator. So accumulator is the very primary functioning register. And then memory address register is when you access main memory, the address is stored in MAR, and based on that, the data is read or written. The memory buffer register MBR is to hold the data between memory. So if when you read the data from the memory, the location address is given in MAR, but when you read the actual data comes from the main memory and then it is stored into MBR. When you write into the main memory, the data from MBR will be stored into main memory and the like. And then program counter is a hold address, address of the next instruction to be executed. The one being executed currently under execution is in IR register, instruction register, and the next instruction to be executed is appointed by program counter. So this is address, program counter is address, but IR is actual instruction under execution. And then for input and output, we have an 8-bit register called the in register and out register. So total, we have 8 register. Here is a very simple architecture graphically shown in marie simple model. So arithmetic and logic unit has a very popularly, widely used register called the accumulator. And then the data is stored in MBR before it's stored into main memory or the result and the like. The MAR, memory address register, is to point the location of the cell in the memory. And then program counter is the address of the instruction to be executed next. The instruction currently under execution is in IR register. So you have an input and output register as well. Then all registers are interconnected. Also, registers are connected with the main memory through common data bus. And then each device on the bus is identically identified uniquely, so that they, based on the control, you can have them communicated. And then in addition to the main common data bus, there's a separate connections between accumulator and the memory buffer register, and the between arithmetic logic unit and then accumulator and the MBR. And this permits the data transfer without using the main bus, which implies some concurrency is supported. So here is a picture for the data bus connections. So between MBR, memory buffer register, and the accumulator and the ALU, so it has its own separate connections. So those three can communicate without using the main data bus. Other than those three to communicate, they have to use the main data bus. So for PC, to indicate the memory location, so PC should use a main bus, and then any other registers cannot use the main bus. So main bus is just uniquely used at the given instance. But however, those three has separate connections. So without using main data bus, they can communicate each other. So this guarantees or supports some concurrency, so that performance could be enhanced out of that.